Okay, in this tutorial, we'll be looking at a microscopic view of glycerin and when it's undergoing a phase change. So I have two pictures here. I have a picture where it's going to be undergoing where it's a non-phase change. So we'll take a look at where the heat energy is going during a non-phase change. So the sample is just heating up on a hot plate. Okay, and then we'll take a look and see where the heat from the hot plate is going. So there's two cases that are happening. Okay, if you're boiling a substance or you're attempting to boil something, there's two possibilities or two different areas where energy is going. When you look at the molecule microscopically, like where on the molecule the heat from the hot plate is entering. So we're so it's during a non-phase change, and then also during a phase change. Where's the heat going? So when it's first of all, this molecule that we're using is glycerin. Okay, and here's the empirical formula is C3, or I'm sorry, the condensed formula C3 H8 2 4. Let's see, 2, 3, 4, 5, 6, 7, 8, and three oxygens. Okay, and as you can see, it's like three carbons connected like that. Okay, and on one of the carbons, this is a CH2 here. Okay, and then it's got an OH on both ends actually. So there's a CH2 OH on both ends. Okay, and then on the middle carbon, it's got an H and another OH on the middle carbon. So my picture here is showing the glycerin molecule sideways here. So um, and as you notice, it has three OHs on it. So it has OH here, it has another OH here, and then another one here. Okay, and then this is the same molecule, but I just made it face the other way so that they could face each other. And so you'll notice that since we have our dipoles here, so on each OH, C to OH, this portion right here, okay, there's a dipole there and a dipole there. So we have a partial negative and a partial positive. Okay, I'm just going to analyze one of these. Okay, to show that you're going to get a hydrogen bond between this hydrogen here and this oxygen here, this one. Okay, and I'm going to show another hydrogen bond here. Now I had to like crisscross them. I couldn't get it like a exact accurate picture here, so it kind of looks like it's crisscrossed on the end ones. Okay, and then you're going to get the same effect here, and then you get the same effect here. Oops, this is not really. I'm gonna have to go like that, and I kind of have to crisscross these. Okay, another one there. So you get lots and lots of hydrogen bonding on this molecule, and in fact, you get so much that the boiling point for glycerin is 290 degrees Celsius. And this stuff is really, really viscous. It almost looks like honey when you pour it. So the viscosity is really good on this molecule. Um, so this is heating up, okay, on a hot plate, and during a non-phase change, all it does is it makes this whole system. It kind of makes it wobble here. Okay, these are like little motional, vibrational energy, little waves that I'm drawing. Okay, so it kind of just makes the whole thing it just makes the whole thing shake. Okay, over and over. Okay, so the whole thing's shaking. And so the energy goes into actually let me make these waves. Can make these a blue color here. Okay. So that blue color, those little waves there, it means the heat energy is going into the kinetic energy of the molecule. Okay, so let's say, you're not at quite at the boiling point. So let's say you're at around, let's say 100 degrees Celsius. Okay, so the heat energy is going into the kinetic energy. It's just making the whole thing wobble. So, what happens when you get to 290? So, right at 290, okay, if it's at 1 atm or standard pressure, standard atmospheric pressure, which is 1 atm, and we'll go on that. We'll cover that topic on the vapor pressure tutorials. Okay, like the definition of boiling point when that happens. So you can affect boiling point by changing the external pressure. But okay, so let's draw our IMFs again. Uh, see there, and then this H to this oxygen, this H to this oxygen. Okay, generally in textbooks and on my PowerPoint slides and on my tutorials, I'll be using dotted lines for IMFs or intermolecular forces, so attractive forces on the outside of the molecule. And then the typical convention is to use a straight solid line for covalent bonds, like that line, for example. It's a solid line. Okay, so during a phase change, the heat from the hot plate it's so what's happening at boiling point is this is being converted into a vapor. So these molecules are going to be leaving this beaker. So what do they need to do to leave the beaker? They need to break the hydrogen bonds. Okay, it's got to break this one. It's got to break this one and this one and this one. It has to break a lot of hydrogen bonds on this molecule. So that's why we see such a high boiling point for this molecule. So the and bonded energy is associated with potential energy. So we'll make a note of that. Okay, so and once all of these are broken, this is able now to leave as a gas molecule. Okay, so and you won't see a change in temperature. So if you're measuring this with a thermometer, so if you have a thermometer in here, in the beaker, you won't actually witness a change in temperature. So in theory, it stops vibrating and the whole system comes to kind of standstill while all these hydrogen bonds, while the heat transfers energy into these hydrogen bonds. Okay, and once these all snap, then this pops out. Okay, the gas molecule will pop out. Okay, and then it's kind of like you keep stretching and stretching a rubber band. Okay, stretching and stretching and stretching. Then all of a sudden the rubber band snaps, and all this potential energy. So all this potential energy here, all the potential energy here, it gets converted into kinetic. Okay, and then it just shoots off into motional energy. So it goes storage, 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 and then boom, it shoots off into kinetic. So making the gas molecule move. So that's what's happening during a phase change. So there's some take-home points here that I'll write. I'll use a red ink pen to write here. So um, the point here is the heat energy during non-phase changes. It goes into kinetic energy. And for these phase changes, okay, so for these non-phase changes, we use the heat equation if we had to calculate how much heat. Okay, so for example, if you had a question that said, how much heat does it take to heat up glycerin? So if you had a question that said, how much heat energy to raise the temperature of glycerin from, let's say, 50 degrees Celsius to 100 degrees Celsius. Okay, to answer that question, you would use our normal heat equation, Q equals mc delta T. Okay, and you would need the heat capacity of glycerin the quantity of glycerin in grams, and then the required temperature change to do that problem. Okay, for a phase change, there is no delta T, so we cannot use this equation. We can't use the traditional heat equation. So we need another variable. We need what is called the enthalpy of phase change. So first of all, let's make a note here and say that heat goes into the potential energy, or PE, potential energy, or PE. Okay, and there's no delta T, so we have to use Q equals, you still have to factor in the quantity. So obviously if you have a lot more, you're going to need more heat. So that's still a factor. So we put M. Actually, usually this is N for moles because typically you'll find enthalpy of phase changes. The typical unit in chemistry, at least, is kilojoules per mole. So you're gonna need your quantity needs to be in moles times delta H. Now this in this case we're trying to vaporize the gas. So there's a different value for the enthalpy of fusion, which is when you melt something or freeze something. So we use N times delta H VAP, the enthalpy of vaporization for phase change processes. Okay, and we'll be going over a problem shortly. So let me move on to the next slide. Okay, and we'll make some definitions about enthalpy of phase changes. Okay, so enthalpy of phase change, it's another physical property of a substance, and it changes with IMF. So you would expect glycerin, which had a massive um, IMF, you would expect it to have a very large enthalpy of vaporization. So let's go through what each one is. So the delta H VAP is enthalpy of vaporization. Okay, and this is when you go from liquid to gas. Um, the enthalpy of fusion is delta H FUS, so this is enthalpy of fusion, and this is going from solid to liquid. Okay, and there's also an enthalpy of sublimation, so delta H SUB. Okay, so this is solid to gas. Um, Now, these are all, so these would all be these processes as I wrote them. So here's a special note. So endo versus exothermic. Endothermic and exothermic. Because you can go both ways, right? If you wanted to freeze something, um, so if I'm sorry, if you wanted to condense something, then you would be going from gas to liquid. Okay, and then if you wanted to melt something, you go solid to liquid. But if you wanted to freeze it, you would go liquid to solid. Okay, and likewise, if you wanted to deposit something, you would go gas all the way to straight to solid. Okay, which is the opposite of subliming. So, and these processes they're the same value, so the quantity will be exactly the same, but you need to change the sign for to put it in terms of this what's happening to the system. Okay, so for endothermic, this is like going from solid to liquid to gas. Okay, these all these processes would be requiring heat. So heat needs to go into the system for these to happen. So You should have positive values for delta H vap, delta H fusion, and delta H sublimination. Now, if you're going the other way, this is always harder to think about on during phase changes. But if you're going, I'm going to write it in the same order, but reverse my arrows. Okay, now if you're trying to do this, then actually, you know what I usually like to do? I actually like to write this one in blue in terms of the surroundings. So when it's endothermic, the surroundings. So this is heat is leaving heat is leaving the surroundings, leaves the surroundings. Okay, and you get positive values for the enthalpy of phase changes. Okay, actually, I should write this one first. So I'll write the okay, and usually it's just those two. Okay, but realize this one also the sublimination one is also could also be something that could happen. Okay, now if you're going the other way, this one's interesting. So heat actually leaves the system and goes out into the surroundings. So I'll write this one in red. So, and when it's exothermic, the system is giving off heat to the surroundings in these cases. So for example, when you freeze something, so when you go liquid to solid, let's say you put a tray of ice in the freezer. Um, so this one's kind of hard to think about because you keep thinking of the system. Well, the ice is getting cold. Okay, so how could that be exothermic? But what you're forgetting is how does the back of the refrigerator feel? There's fans in there, and what's happening is it's pulling all the hot air from the contents out into the back. Okay, there's also condensers. There's like a gas that goes through the tubes and it condenses and reheats. It condenses and boils and condenses and boils and vaporizes, and it keeps going through these tubings in the back of the refrigerator in order to remove heat from the ice cubes. So the back of your refrigerator ends up feeling hot because heat is being removed from the liquid water in order to freeze it. Okay, so your surroundings will end up feeling, so the heat goes to the surroundings and the surroundings end up feeling hot. Okay, another simple one is when you blow on your hands, you're actually doing this conversion. You're going from gas to liquid. So you breathe out gaseous or water vapor. It comes out of your breath. Okay, and when you enclose it, you give it a spot for it to condense. And then how do your hands feel when it goes gas to liquid? Your hands end up feeling hot or warm because you just did a phase change. You went from water vapor to liquid water. So your hands also feel a little bit moist from that phase change from the water vapor from your breath going to liquid. Okay, so this also happens. Um, so this another example of this one, a practical example, is when you sweat, like you're playing basketball and you sweat. So you have liquid water, basically, essentially on your skin. Okay, and how do you cool down? Well, when the sweat evaporates, so when it goes liquid to gas, it removes heat from your skin. And how do you feel? You end up feeling cool because heat left your skin, so you end up feeling cool when that happens. Okay, so in terms of problem solving, okay, if you notice that you're doing this direction for phase change, solid to liquid to gas, if you're using the enthalpies of phase change in an equation, okay, then the values you need to be using are should be positive. Okay, if it's going this direction, okay, from gas to liquid to solid, then you should be using negative values. So your value for um, enthalpy of fusion will be negative, and your value for enthalpy of vaporization will also be negative. Okay, so that concludes our tutorial. In the next one, this is a lot of background. In our next tutorial, we'll be going over problem solving using. Let me go back to the previous slide. So we'll be solving some problems using these, and hopefully we'll clarify when to use which one. Okay, and it kind of all depends on the problem. So look for that in our next tutorial.